the second quiz, is a bit of a combination of the two chapter sections 5.3 and 5.4, recursive function and algorithms, in the following sense. So I'm going to go two problems, and the quiz problem will be very similar to that. Okay, because there are many different things you can ask, of course, but this is what I'm having in mind. So let's start with perhaps an easier case. And so suppose we have an algorithm, the following algorithm. So again, I have to write down my algorithm. So we have procedure, and the procedure is going to be called square. You'll see why. Square, and it's for n, where n is an integer, a natural number. Okay. And what does it do? It says, as always, very typical in recursive algorithms, is that if n is 0, then return. Then return the value, the value. So let me write it up. Oh no, that's not what I want to do. If n is 0, then return 0. Okay. And then the induction step, if you want, recursive part is else return the following thing. Square of n minus 1 plus 2n minus 1. Okay? So let's explore first what this is. What is the square of 2? Okay? So square of 2, what is that? Well, n is 2, and therefore we have to carry out the main step here, the main recursive step, this one here. So what we get is that this is equal to the square of 1 plus 2 times 2 minus 1. Remember, I replace in this formula n by 2. Okay? So that means that it's the square of 1, 4 minus plus 3. Okay, so now what's the square of 1? Okay, so n is 1 now. But again, we have to carry out the main step, the recursive step, because n is still not 0. And that means that this is equal to the square of 0 plus 2 times 1 minus 1. Okay, again, replacing in here n by 1. Okay, so n minus 1, that is a 0 here, and that's a 2n. Okay, so this means that this is square of 0 plus 2 minus 1 plus 1. And then finally, square of 0, that one we know, I'm going to use different colors now. This is the red is when I did the actual calculations, is 0, because we are in this case here now. Okay, so the algorithm stops and returns a value. Okay, so using that I can plug that in, and I see that this is 1. Using that I can plug that in, and I see this is 4. So the square of 2 is 4. Okay, might guessing a little bit more and more what square is. Well, here's now the main problem. I haven't formulated the actual question yet. The question is, so use induction, or perhaps strong induction. I'll put it here between parentheses. In this case, induction will work, but I'll give you an example where you need strong induction to show that square of n is equal to n squared. And then now you, I guess, figure out where the name square comes from. Okay, it's the square function. Okay, so how do we do that? So proof, well, the two steps. There's a basic step, that is n is 0, and so now the question is the square of 0 equal to 0 square? Now the square of 0 by declaration, if you want, right, by this part here, is 0. So this is 0, and so yes, this is clearly true. Basic steps are always extremely simple. I shouldn't say always, but in many cases they're extremely simple to verify. Induction step. And since we are doing recursive functions, induction is very often starts from n minus 1, and we go trying to prove it for n. So assume that the formula is true for n minus 1. So assume correct for n minus 1, i.e. meaning, this means what? Well, this means that in this formula I can put in n minus 1, it is true. Okay, so that means that the square of n minus 1 is n minus 1 squared. To show that the square of n is n squared. So let's put a question mark on there, we don't know yet. Okay, so here's our proof. When you do proof by induction, always set it up in this. Write down what is it that you're assuming, write down what you have to show, and then prove it. Okay, so the proof, the square of n, and again, since we have to prove it, I keep writing these question marks on top of it. Is this true? Now, what can we do? We can work with the left-hand side because we have a recursive algorithm that says what square of n is in terms of square of n minus 1, or in general of the function in terms of the previous values. And so what we of course dealing with is this formula here, because I should have perhaps said it here, this is now for n at least 1, because we dealt with the n is 0 case. Okay, so that this numbers n minus 1 is well defined. Okay. Okay, what is that? So the square of n, so we have a big equal sign here, by the algorithm, the square of 1 is the square of n minus 1 plus 2n minus 1 plus 1 minus 1, 2n minus 1. Okay. Now, there is more. No, we have more information because we also have this information. Okay, let me put it perhaps in green to tell you this is something we know. We know that this is true because we assuming it. That's part of an induction. That means that we can replace this square of n by n minus 1 squared. Okay, and then the rest is plus 2n minus 1. And then the final step is often a little bit of algebra. So let's simplify this thing. N squared minus 2n plus 1, the double product formula, plus 2n minus 1. The two n's cancel, the n minus 1 cancels, so this is n squared. And then at this point we can say, yes, we have achieved our right-hand side, and we are done. Okay, so let me give you an example of a little bit more complicated guy here. Give me 1 sec here, I have to double check. Where did it go? Okay. Yeah, okay. Okay, so okay, let's look at the following procedure. I'm going to define a function. Okay, I'm going to be a little bit lazy. I hope you're okay with that. I'm going to repurpose my it's so cumbersome to write, to keep changing here the. Okay, so the procedure here is, I call it pfip of n, and it says that if n is 0, then return 0, else, oh okay, there is an intermediate step here, so let me, okay, I have to do this, I'm gonna put it here, else if n is 1, then then return three, else return the following: p fib n minus 1 plus p fib n minus 2. Okay? And then what I want you to know, what I want to do is show using, and you need strong induction here, show using strong induction Now, I'm not going to ask you to actually give a formula for this thing, because actually the formulas are quite complicated, but they exist. But prove strong induction that the following formula is true: f1 squared plus f2 squared plus dot 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 plus fn squared is equal to fn plus 1 for all n at least 1. So not for n equals 0. We could have added that, but we don't do that. Okay? So this is what you need to show. Show using strong induction that is the case. Okay, it's a proof by induction. There's two steps. The basic step. So here's the proof, right? The basic step is, well, now n is 1 here, right? So n is 1 because, remember, we're claiming this to be starting from n equals 1 to be always true. N equals 1. So what does this now say? Now remember, what you should look at what the left formula says. It says you sum up the first n elements in this sequence. In this, sorry, I wrote p fib and then I wrote f. Sorry, I always mean f. Let me make these guys all capital F's here. I don't know where my so it's capital F. That's yeah, and then I wrote the index. Sorry, I copied it from a different problem, and that's why I got a little bit. Okay, let me rewrite it. It's f1 squared plus f2 squared plus dot 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 plus fn squared is fn times fn plus 1. Sorry. Yeah, there's sometimes people write if a function as a real function, but sometimes they think of it as a sequence indexed by an index n. But since I'm doing a function, let's write it in a function notation. Okay, basic step, n equals 1. What is this? Well, if n is 1, then on the left-hand side, so the left-hand side is f1 squared. And what is the right-hand side? The right-hand side is f1, f2. And the question is, are they two the same? Now, notice that we have to do a couple of things. We have to first find out what is f1. Now, f1, according to the algorithm, is 3, right? Because that's the part where the algorithm gives you the answer right away. So f1 is 3. But what is f2? f2 we don't know yet. The algorithm has to still calculate this, right? So, because we are now neither in these two, we're not in these two cases, so we're in the else case here. So it says it is f1 plus f0. Now, luckily we know what these two are. f1, we already said is 3, and f0, it's from this one, it tells me that if n is 0, then the outcome is 0, so f0 is 0. So this is 3. And so now the question becomes, is 9 equal to 3 times 3? And that is, of course, the case. So that's the basic step. You see, there's a little bit more work that I have to do here. So now the induction step. So suppose true for all values between 1 between 1 and n minus 1 to show true for n. Okay, we can take this point of view that it is better start from n minus, assume something about the previous values and call them n minus 1, n minus 2, and so on, and then prove it for n. The reason being because that's how recursive algorithms work. Not functions, but algorithms are set up that way. Okay, let's see what this means. Okay, we have a little bit of junk from before. Let's get rid of that. Okay, so proof. What is it that we have to show? We have to count. Let's write out what we need to show. We have f1 squared plus up the way plus fn squared. And the question is this equal to fn times fn plus 1? Okay? Okay, so what do we do? We have f1 squared plus f. Let's break this down with one more term here, right? This expression is, they're dots, but that means there's some stuff. I'm breaking it down to a part that I kind of know something about. Because I know about this one, I know what the truth is. Why do I know what the value is? Because this is one of the cases between 1 and n minus 1. So this is the case n minus 1 actually, and I know that it is true. So I know this is the induction hypothesis. So the induction hypothesis, IH, tells me that this is equal to f. Now be careful. What it says here is that if you take the sum of the squares of the first n many, then it's the n times the n plus 1. So here we have the n minus 1 many, so this is equal to fn minus 1 times the next one, fn. Okay? So that's what we have. That's that, and then we copy the other one. I'll go back to black here. So this is still the term we don't have. Okay, so now we're going to have to, we are not there yet, right? This is not the form that we want, so we're going to have to manipulate a little bit. We have a term fn and a term fn here. I'm going to split them off, fn, and what I'm left with, fn minus 1 plus fn. Okay. Now, what is this function? Well, let's look at what the procedure does. So we don't, okay, let's stop here perhaps. So normally, perhaps I could have not done, let me not do the last step, because, okay, you might say, why did you do the last step? It might be a little bit less clear here, so why do that? So let me wait for that. It's a correct step, but let me wait. This is a situation where I said we normally work on the left-hand side and we want to go to the right-hand side, but that's not always possible, okay? So now I have to start thinking a little bit more about the right-hand side, okay? Because look at what I have here. At this side, I have fn and fn minus 1. So that's this fn is fine, fn minus 1 is not part of here, and here's an fn plus 1. So I have to rewrite this one, because I should not have something that involves n plus 1. On this side there is no n plus 1. Luckily, I know what that is, because I can apply the algorithm to that. Let's see, what is fn plus 1? So I'll do this here, I'll do this in red perhaps. So fn plus 1, so this is the algorithm with n plus 1, okay? So that of course is, because n is at least 1, n plus 1 is at least 2, so these two cases are not happening. We are really dealing with this case here, okay? And what this says, if you ask me what the function is at a certain natural number, well, you add the previous two numbers up. Okay, so let me see what we get. So this is the previous number is n, and the one before that is n minus 1. That's you have to think flexible, right? This formula, if you think about it, it says the value of a function, of this function, is the value 1 less and the value 2 less. Okay, so the value of this function is the value 1 less and the value 2 less. Okay, so this is what we have now. So let's plug that in here. I go back to black here. So I have now that this is fn and that this is fn plus fn minus 1. Okay, and let's expand this now. This is fn squared plus fn minus 1. And so we see now that this is equal to that. Remember, this is it's easier to see now that they're equal this way. The other manipulation was a bit weird, perhaps. Why did we do that? But now we see it, so we have a proof. Okay, so I said we need strong induction. I actually was not true. So induction was enough here. Why did I propose strong induction? Well, because I'm doing a function that is recursive on two previous values, and very often you need the previous two values for that. So here's an example where you see that although this is how this function works, not everything needs necessarily strong induction. Induction would have worked too, because that I have only used the induction hypothesis for n-1. This is where I used it, okay? So let me make it explicit here. This is the induction hypothesis for n-1. That's what I've been using. Okay, so this, granted, is a little bit harder, but the previous one, I hope, also is something that is more straightforward.